Welcome to the video series on contact mechanics in the course M7033T, Scientific Computing with Applications in Tribology. My name is Andreas Almqvist and I work in the Division of Machine Elements here at Luleå University of Technology. So this is the fifth part of the fourth video lecture on the application of Fourier techniques and multi-level multi-integration. And this one is all about the elastic deflection and the coupling to the circular convolution so that we can accelerate its computation by means of FFT techniques. This part starts with a recap of the elastic deflection, the definition of this one, and then we will look particular into the exact operations involved in evaluating it in discrete form. We will compare this with the evaluation of the circular convolution, and we will by means of this see the similarities, make use of them to extend the elastic deflection, the representation of the elastic deflection, so it can be represented by the circular convolution, and by that lending itself to the application of fast Fourier transformation technique to evaluate it in an accelerated manner. And there, okay. But we saw that they were perfectly exactly the same, and we were happy to some sense, I would say. Now, it has come to the point where we are going to start to see if we can treat the elastic deflection as a circular convolution in some sense. So let's have a retrospective look at the Boussinesq deformation equation again. So it's just defined by K, Kp, the integral of Kp, and K is of x minus x prime, and whether x prime is a dummy variable, and we integrate over that one. We can think of we can define k in 1D and we can define k in 2D like this. Then we have to generalize the thinking a little bit in 2D when we write x minus s, and therefore I have used boldface x and s because they are not just one directional now, they are vector valued. And then when we discretize this, we know, and we have seen this many times now, that we get exactly this expression in summation formulation. But we have now a kernel with an absolute value between I and the summation index j, because of that deformation of a half space in 2D or 3D is only dependent on the distance where the force acts. So it is sure similar to a convolution, but it's not exactly the same as a circular convolution because of that absolute value between the indices. So let us look. If we have K and P are vectors of length 4. So I is from 0 to 3, and then we will sum j from 0 to 3 to obtain the deformation for each j. For each I, sorry. So we have the vector p here, p0 to p3, and for I0 we know exactly what the difference is, we know exactly what the absolute value is, and the same goes when we increase the summation index, and therefore we can easily just obtain the value of k, which we should multiply with p in order to obtain the value for the deformation at that point. Okay, let's compare this. So if we now have a convolution V between G and P, and G is now circular vector here, which we circulate with a modulo 4, then we can clearly see that these two multiplications would be different if we use the same vector for k and g, because we have k0, k1, k2, k3, and in the other case we have k0, g0, oh sorry, g0, g3, g2, and g1. So they would be very different, okay, if it was not just a constant value, the same value for all the indices. And of course, when we increase now the index I one step, the circulation on the right side is we know exactly how it circulates, but look what happens when we increase the number I in the left hand side, in the real elastic deflection summation example. Then we actually move the first element one step forward, but we move the second element to become the first one. And this symmetry, so that so that a load at one point causes the same deformation to both sides of it. So now it's completely different, and this goes on and on, of course. So when we increase the index I, we shift the vectors in different ways. We circulate the right hand side, and we shift the left hand side to be symmetric all the time, and therefore we have two different matrix vector multiplications. On the left hand side we have a circular but symmetric matrix, and it turns out that this one is actually a Toeplitz kind of matrix. The other one is also a Toeplitz kind of matrix, but it's ordinary circular in some sense, so it's just plain circulation, it's not including this symmetry. What we can see if we look closely is that the lower triangular parts of these repeats the indices the same way. So if G and K would be the same vector, the lower triangular parts of these matrices, they would be identical. MATLAB example to illustrate this: we take the same vectors once again, and what do we get when we Toeplitz H times our transposed F and then transpose the results? Well, we get the value 553. We could have, instead of using the built-in MATLAB command Toeplitz, define the matrix ourselves. And what would that matrix look like? Well, here we can, since it's symmetric, we can think of it either in row or column way. So if we set up the first row or column, it would be 1, 2, 3. And if we set up when we set up the second row or second column, it would be shifting 1, the first number 1 to the diagonal position, and then shifting the number 2 that was sitting one step below to the third row to be a 2 there. So then we have on the second and third row we have a 1 and 2 in the second column, and then we have to have a 2 in the first row because we want the matrix to be symmetric. And we continue. And this is how it's generated. If we use the circular convolution example, in this case, we already know the answer would be 237, and it's, of course, quite different from 55. Did I say 237? 273 should have been. And then it's very different from 553, of course. So using circular templates is actually also a possibility. It's a little bit tricky here, but having H, we can actually take H and then a swapped order type of H and give those two as arguments to the templates function in MATLAB, and then we generate the same matrix as we know we would have for a circular convolution, and therefore the result will be the same when we multiply it with F. 273. Again, alternatively, we could define it explicitly like we did before. So, in order to apply the FFT technique to accelerate the computation of the convolution, or accelerate the computation of the elastic deflection, we need to extend the kernel of the elastic deflection in a specific way. And if we do, as we will see in this, if we find this specific way of doing it, we can perform the FFT scheme to accelerate the computation of the elastic deflection too, even though it's not a circular convolution to start with. So we have talked about this several times. When we view the deformation, we know that it doesn't matter location wise, it's just the distance to the point where we apply the load that causes a certain amount of deformation, and therefore we just generate the kernel of the elastic deflection by the same symmetrically reflected base vector, just shifted one step, going from first column to the last column, from left to right. And if we compare that to the circular convolution, and we have the same signal, the first column it would be the same numbers, but what happens when we circulate in the circular convolution case, then we realize we only preserve the lower triangular part. They will be the same, it's clear, but the upper triangular part will be different due to the periodicity, and therefore we first now consider the kernel. Well, it's the first row or first column of the elastic deflection kernel consists of k node up to k minus 1, and then what we do is that we actually will reflect this, shift it, we add a 0 at what will be the Nyquist frequency again, and then we have just flipped a copy of the first part but skipping the absolutely first number k node on the other side. In this way we get a new extended column or row for our kernel, which is double the size, it's 2n long, and it turns out that we can disguise this extended formulation of the deflection as a circular convolution like this, and let us now denote this extended deformation by u tilde, and then we will, in order to produce that result, we also need an extended pressure which we denote p tilde. And here m, now the summation goes from 0 to m, and I is from 0 to m, and m is actually 2n minus 1. So let's see. We need to remember that the elements of C, which are ordered as C0 followed by the last element C2n-1 and then counting down to C1, contains the values of K0 to Kn-1 as the first elements, and then the 0, and then starting from the end of the first part Kn-1 and counting down to K1. But we can also think of it as three parts. First part, which is n-half, a middle part, which is n, and a third part, which is n-half again. And it is useful to think like this because this is the way we would zero pad our pressure. We would make the pressure 0 at the first n indices and at the last first n-half indices and at the last n-half indices. And then we have the pressure in the middle. Now let's have this concrete example with n4, so m is 7, and then the extended deflection in summation form is expressed like this. So now we have the difference between the indices I and j, modulus 7. If we now consider the pressure, and then we have the underneath it, we have the kernel for the circular convolution in C, and then we have revealed the values of it in the third row, which is actually the values which we find in the elastic deflection deformation, elastic deflection equation. Yeah. So let's see now what happens when we circulate these kernel vectors a few steps. I have marked out here the position of the 0, and now you can see the circulation scheme looking like this. And if we then move one step, you see you can easily follow the 0 here, and we can of course also follow all the other indices, and we can see that the C1 index is now the first one in the C row, and we have K1 is the first one in the K row, and we continue with. So this is what it becomes for I equal 2. And actually, if we stop here and have a look, we can now see that within this green window, we have on the bottom row actually the first row of the kernel matrix for the elastic deflection. And as we continue, you will see what happens. And now, at this stage, what we actually find here, if we perform this multiplication, you can clearly see that at this point, the multiplication will be P0 K0, P1 K1, P2 K2, and P3 K3. Now remember, this is exactly the first discretized value, U1, for the real elastic deflection. And if we continue to circulate these vectors in the same manner, the next 3 revolutions, and in this matrix vector type multiplication will actually be captured in this center frame, and it will render precisely that matrix vector multiplication. So if we write this in summation form, we get that the real deformation is just the extended deformation evaluated in shifted set of discrete nodes. So ui is extended u tilde I plus 2, and we just carry out the summation with the extended kernel multiplied with the extended pressure P. And here we, of course, we cannot evaluate ui for more indices than from 0 to 3, because if we did, we would get extended deformation values which are not true deformation values. So these are the true deformation values. In matrix form, well, we've seen this now many times before. So for this system where n is 4, we get a 4 by 4 matrix kernel which multiplied with the pressure then gives the deformation, and that's exactly what we extract from that summation. And in general we can write this, of course, like this. So that number 2 in the above summation is just n half, and number 7 is just 2n minus 1. So in general we get this summation, and we can evaluate the real deformation by taking the indices I from 0 to n minus 1. So the important thing now, it's that the circular convolution, the extended one, in terms of deformation, it ensures a subsequent DFT analysis or application. So we can apply the FFT, and therefore we know the transfer function. We apply the FFT to obtain it directly from C, from the extended kernel, and we apply it to obtain the Fourier transformation of the pressure, P, the extended pressure, P tilde K, and then we can compute the extended deformation, U tilde K, in terms of its Fourier transform in the frequency space. And then we have seen this before, and we can formulate the transfer function as the DFT of the extended kernel, and we can divide the extended kernel into 3 bits like this. So we have an n half long bit in the beginning, an n long bit in the middle, and an n half long bit in the end. And the reason for doing that subdivision of it is that we extend the pressure in this way. So we have n half zeros in the beginning, we have the n values of P, and then we have another n half values of zeros to form our extended pressure. And when we do, we all know that this is how we carry out the actual convolution, and hidden behind the C's we have the K's, which are the original coefficients from the deflection or the deformation matrix kernel. And okay, here I just painted the number of elements over, because we of course have constructed it in this way instead. Just to recall what we have in our transfer function, it's actually the first n values are actually the k values, the real k values for the deformation, and then we have that 0 at the Nyquist frequency, and then it's flipped or mirrored version of the matrix kernel to the rest of the right hand side of that vector, which we then DFT to obtain the transfer function. So, summary: we have the transfer function, we have the extended pressure, we get the extended deformation in the Fourier space by just multiplying these two. In MATLAB we will do that pointwise, of course, and then we can extract, or we can compute the extended deformation u tilde k by taking the inverse Fourier transformation, and then we evaluate the extended deformation in the values I plus n half for I equals 0 to n minus 1 to obtain the real deformation. We've seen this before. It's just the MATLAB code to construct and to compute the matrix, the deformation via matrix vector multiplication. And if you do, we have seen this plot before, you get the deformation like this. If you just withdraw or subtract the first value of it, so it starts at 0, and that's just for comparative purpose. So now if you then via the DCFFT method you compute the first row of your kernel. Here I have chosen to call it the DC1. So it's the discrete convolution row 1, and it's obtained by the values that we had before. We have already defined the C1 vector. We take that vector, we add a 0, and we add a flipped copy of it, but not all of it, to have it correctly defined. Then, okay, this was not really the scaled version, so we need to multiply by minus 1 over pi, and then we FFT, and we take only the real part because we want to get rid, and then we get the transfer function DCH. We define the extended pressure very conveniently by just setting a vector of zeros of length n½ in the beginning and the end of the P that we already had defined, which is also in this particular case exactly the Hertzian pressure. And then we compute the extended deformation by means of FFT, UDC FFT, by a multiplication, pointwise multiplication with a transfer function and the Fourier transformed extended pressure. Then we invert this by taking the IFFT and getting rid of the imaginary noise with the real, and then we just extract the set of values from the extended deformation, which are the real deformation values. We plot this, and we subtract the first value to get it 0 to begin with, to have a good comparison. We also generate this error measure, and when we plot, the reason for doing that, of course, is because we're going to show that it's numerically exact, and when we plot them, we just see through between the dashes in the red line, which is now representing the DC FFT computed deformation, and in the dashes in that red line we see through and see the values of the standard deformation carried out by or standard way of carrying out the deformation by matrix vector multiplication, which is plotted in black, and visually they are inseparable, and therefore we have this error measure to show that they are actually of machine epsilons. Recall that we were also working with Vestergaard's solution. He found that it was possible to actually find a closed form expression for the integral of the deformation when we when we viewed or took the pressure as a sinusoid or cosinusoid. And this method we refer to as continuous convolution, and then plus subsequent DFT method, and therefore we get what we get here is actually very accurate as long as we do not have any noise or any disturbances. And unfortunately we do with the Hertzian pressure distribution, because if you think of the Hertzian pressure distribution, it's very difficult to resolve the Hertzian pressure distribution exactly where the positive values begin, because we have an infinite derivative there, or a very large derivative numerically also, and this will give rise to problems here. So in order to have a good result, we would actually have to take that Hertzian pressure and then adapt a Fourier series to that one, which would then not really be the Hertzian pressure, but nearly, and then that one would actually give us a good result here, but it wouldn't be exactly the same result. So, well, if you don't do this and you just take your pressure, you extend it, you generate your transfer function, and then you carry out the subsequent computation, which are exactly the same as in the DCFFT method. You can, of course, get a comparative result again. And here I have added something here. We have an extension here. So, and this extension, this extra extension, is therefore the aliasing. So, if we actually increase this ext number from 1 and further, we will see that we get a better and better representative of the deformation computed this way. But let's first look at it without any extra or additional extension via the ext. It's just 1. Then we have in black, and then in dashed on top of that, we have in black we have the standard way of computing deformation, matrix vector multiplication. In red we have the DCFFT dashed, and then in blue we have the CCFFT, and we can clearly see that there is a difference. If we had not seen or had not had the real solutions to compare with, we would probably have believed that this was correct result, because the shape is pretty near, pretty close, but it's really not exactly the same, and the error is quite big. It's order of -2. And if we then increase the number, if we then increase the extension number from 1 to 2, we add a double amount of nodes, so we have much higher frequencies to represent things within the frequency space, and therefore we can represent the Hertzian pressure in a more accurate way, and we get more accurate computation of the elastic deflection. And if we increase it even further, of course, we get better and better. I'm sorry for not updating the error down there, but the error is closing in definitely. So this shows that really the preferred methodology is the DCFFT one, and this one is more for just analysis and such purposes, because you can clearly find out a lot of characteristics about the deformation by means of the analytical solution for the transfer function.